Cool. Okay. Yeah. So as you're aware, there's been lots of kind of great success stories for geometric deep learning, and that's been kind of driven by the many sort of domains where data kind of can live on. So stuff like molecules, meshes, manifolds, and all sorts of things. But in this talk, what I sort of want to challenge the kind of idea that geometry is enough. So why am I saying that? In kind of differential geometry or in like mathematical physics, we have a whole bunch of kind of structures, and there's a whole structure hierarchy. So kind of on the left side, we have what's called like a topological space. So this is just a set where we also have some sort of notion of neighborhoods. So for instance, this point P you see on the left, it has this kind of yellowish neighborhood around it. And that's all we kind of know about this sort of structure. And moving kind of to the right, we kind of have more structure. So we can have some restriction where we also have these neighborhoods around each point that look like a flat space, like a Euclidean space. And this is what this kind of map phi is showing. It's kind of mapping this neighborhood U to something like a circle or something like that, like a disk, sorry, in R2. So locally, everything kind of looks like Euclidean. And you can see the first structure we were talking about. So at the point P, there's actually no neighborhood that looks Euclidean, just because it looks very strange. And basically, the space on the left is not the topological manifold, but the space in the middle, it's called a topological manifold because it has these properties. But now, these topological manifolds, actually, the structure is still not enough because, for instance, if we want to talk about kind of things like smoothness, so when kind of a surface looks smooth, clearly the thing in the middle doesn't look smooth. Kind of these topological properties or structures are not enough to talk about these things, because topologically you can show the thing in the middle is equivalent to the surface you see on the very far right. But clearly one is much more smoother than the other. So if you want to talk about these things, you need even more structure. What we kind of end up with is what's called like a differentiable manifold, or simply what people usually call a manifold. And it's only at this stage, when we're kind of on the far right of this diagram, that we actually have, like where geometry kind of starts. Once we're in this space, we have like tangent spaces to the manifold, and we can do all sorts of geometry. But many spaces, actually, they're not topological manifolds, or even if you're a topological manifold, there are some very kind of strange looking spaces where you can't put this kind of smooth structure on top. I see there's a question. Is the arrow in the third diagram pointing inside or along the plane? So here the arrow is just meant, oh, do you mean like the tangent space one? So yeah, like if you mean about this kind of red area, that's kind of just a tangent vector, and the red area is just the plane tangent at that point, basically. There's just the tangent space. All the vectors are kind of tangent to the surface there. That's what it's meant to show. Anyways, these kind of mathematical details are not super important. The big point is that you cannot always do geometry on any sort of space, because you need to have all these structures, and sometimes it's very hard to get there, or it's even impossible. And this actually led to some dilemmas in geometric deep learning. So Michael Bronstein was remarking in a blog post that graphs are kind of special because they're the only kind of space that shows up in geometric deep learning that doesn't have like kind of like a continuous equivalent, like a manifold equivalent. So if we talk about grids, we have like just the plane as an equivalent. If we have like a mesh, we have the corresponding manifold, the mesh approximates. But if we have a graph, what's the manifold? And there is no manifold, because graphs are actually not even like topological manifolds, and talking about smooth structure is even further from that. So, like, what should we do? And this is kind of like a limitation of geometry in some sense, because it's much more difficult to apply geometry on graphs. I'm not saying it's kind of impossible, and there's lots of interesting research for that, but it's not like it might not come naturally just because of these constraints. And what I'm suggesting in this talk is to take a topological perspective. So what does that precisely mean? So in topology, we talk about these topological spaces, so the sort of things you saw in the first slide with the various surfaces. So a topological space is just a set, but it has some structure on top. So it also has this collection T of subsets of X. And these elements of this collection, we call them open sets. So basically, we just define some sort of open sets that kind of generalize the notion of like an open interval or things like that, but to kind of arbitrary sets. And these open sets, they must satisfy some axioms. So the empty set and the space itself are open sets, and they're part of this collection T. And the second requirement is that if I take like two open sets and I take their intersection, that should also be an open set. And also if I take two open sets and I take their union, then I also get an open set. And here's like an example of a space X that's kind of abstract. And I've just put here like just a bunch of open sets on the right, and that actually forms a topology. So that forms a topological space. So there's this open set U that looks like this reddish color. There's this open set V, and then there's their intersection. And obviously there's also the whole space that is an open set. And the intuition is that these open sets, you could think of them as neighborhoods. They kind of provide some sort of local neighborhood in some sense for the points inside them. So we can talk about the neighborhood around the point by kind of identifying some open sets around that point. Okay, and what I'm suggesting now to do is to look at graphs perhaps in a new perspective that you have not encountered before as topological spaces. So what does that mean? Is we're gonna kind of, if we just think of the graph as like a set of points, we can put some open sets on top. So for instance, for each node V, for instance, like here, we just use all the incident edges and the point of the node itself, and that will form like an open set. So this UV. Similarly, for the other node U, we have this kind of blue region that will be the open set corresponding to that node. And then for this edge in the middle where these open sets intersect, if you remember from this axiom, the intersection should also be an open set. So this edge in the middle will also kind of constitute an open set. And yeah, once we have this, we also need to specify that all the unions of these things will also be open sets, because otherwise, we break the assumptions we were mentioning. So that's the perspective we're taking. And in what follows, we'll see how this perspective can help us understand and develop better graph neural networks. And in particular, we're looking at how we can use this perspective to bring some new insights and solve some problems regarding to heterophily and oversmoothing in graph neural networks. And that's something I'm going to explain in a second. So the setting we're looking at is node classification. So essentially, we have a single graph, and we want to classify the nodes of this graph. Some of the nodes are labeled. So we have these red and blue nodes that are labeled, but there are also some nodes that are unlabeled, and we want to label those basically. But we want to, in training, we'll use those that are labeled and all the features of all the nodes, which live in this feature matrix X, just kind of the classic setting. And first, let me mention this oversmoothing problem. So what is that? Essentially, people notice that for certain types of graph neural networks, for instance, graph convolutional networks, if you just stack many layers on top of each other, you'll see that as the features kind of evolve from one layer to another, they are getting progressively smoother or more similar to each other. And that's obviously bad because we want to classify these nodes. So, if everything becomes very similar to each other, we can't separate these features because they all look kind of the same. So we can't distinguish the classes anymore. And there are some kind of proofs for why that happens. But anyways, we're going to look more into that. The second problem, which is related to some extent, is the heterophily problem. So it was observed that many graph neural networks actually don't do that well when the graph is what's called heterophilic. So that means the graph tends to have connections between nodes that have different labels. And in general, like most graph neural networks, they work well when you have the opposite. So kind of nodes in the same class tend to be connected, but different classes tend to be less connected. And here's a diagram from a recent paper where you can see that GCN, for instance, when the homophily level, so that's the x-axis, so at low homophily and high heterophily, so that's the left side, the performance is pretty bad, but as you go to the right, the performance increases. So as you increase homophily, performance gets better, and there's already some existing methods that have been kind of improving over GCN and kind of doing better in this kind of low homophily regime. And these are kind of the color lines you see here, but there's still kind of a gap to be filled. All right. Now, let me tell you a few words about heat diffusion. So first, just some notation. So we have a graph, we have a degree matrix, we have adjacency matrix, and the normalized Laplacian, which is just that formula you see there. So identity minus the normalized adjacency, and the node features as usual. Now, what I want to mention is that heat diffusion is a very simple process suffering from oversmoothing and these heterophily settings. So why is that? I don't know if you ever saw like a visualization of heat diffusion, but what you can imagine is kind of like you have some temperatures over your graph, and what happens over time, these temperatures kind of become more uniform as time progresses. So like hot regions will become colder and cold regions will become hotter, and kind of everything stabilizes around like some kind of average temperature. And you can see why oversmoothing and heterophily show up in this process, right? Like if I run this infinitely long, everything will converge to the same temperature and everything looks the same. So that's exactly what happens in oversmoothing. And with heterophily, if you have lots of connections between kind of hot and cold nodes, you see their temperatures kind of balance out very quickly and they become kind of the same representation. So you actually make things in different classes to have the same kind of temperature and you can't distinguish them anymore. So it's kind of the worst model you could think of if you really want to kind of have problems with oversmoothing and heterophily. And let me show you something very interesting. So if we discretize this differential equation and we just use like a time discretization, we obtain something like here. So the features at time t+1 are the features at time t minus this Laplacian times the features at time t. Now we can also simplify this a bit further by just using the fact that x is a common factor here, and we obtain this expression in red. Now, what's very interesting is that if you remember the graph convolutional network model, which I think it was introduced in a previous lecture, but in any case, it looks like this. So that's how it combines the features and the adjacency in this formulation. And W here is just a weight matrix. This sigma is just a nonlinearity. Actually, by just using just some simple algebra, this normalized adjacency, just from the definition, it's actually the red part we were seeing before. So this I minus delta 0. So you can see that graph convolutional networks, essentially, they're like heat diffusion or very similar to heat diffusion, but we've just put some extra elements on top, like this weight matrix and the sigma. So in some sense, it's not really surprising that graph convolutional networks have a problem with heterophily and oversmoothing, because they're actually built around this process that's doing very badly at these things. Now, the question we are trying to answer in this paper is, can we make this diffusion process, so heat diffusion, can we make it more advanced and then build like a better graph convolutional network or something of that kind? So how can we make this diffusion process more powerful? And the answer lies in these mathematical objects that come from algebraic topology, and they're called sheaves. So let me give you just kind of a very brief introduction to this. We're not going to go in any details, but essentially sheaves are just a way of keeping track of some data we attach to the open sets over topological space. So if we have a topological space like here, this X, we have some open sets in this space. And what we can do, essentially, we can just glue some data to each open set. So we have these f of x, f of v, f of u, and so on. So yeah, just imagine this kind of flags as some sort of data, like a vector space or something of that kind. And then what we have, if we follow these arrows, is kind of a way to restrict our view to like smaller regions, right? So I have this data over this big region, but if I have some subset, let's look at how that data looks in that smaller region. So you kind of have this way of kind of ensuring data consistency and looking at smaller regions. That's kind of the idea, and it just says what I've just said anyway. So now what we can do is by just adopting the perspective I was mentioning in the beginning, where we think of the graph as a topological space, we can obtain a sheaf over graphs. So what we can do is for each of these open sets associated with the nodes and edges that I was mentioning, we can just put the vector space. So just kind of stick a vector space on top of each of these open sets. And then what we have between these vector spaces, these are the arrows you were seeing in the diagram before, we would just have some linear maps. So that's all we have. So whenever there's kind of like a node or like this open set that's bigger, and we have like an open set that's smaller, like the edge open set, we would have one of these linear maps, for instance. And now, strictly speaking, this is not yet a sheaf, since we have not specified what happens on all the open sets. So these are just kind of some of the open sets of the space. Remember that we can also have unions of these open sets. And we haven't actually said exactly how these vector spaces look like and how these maps look like. And that's kind of an entirely different story. But fortunately, there are these things called cellular sheaves. So these are kind of someone thought about these kind of things, and they actually already defined properly sheaves over graphs, and they kind of look like this. So this was just kind of a way to motivate this definition, but from now on, just kind of think about this definition, and you can forget about kind of these continuous sheaves I was talking about before. So what are these? So essentially we have a graph, and now instead of just putting things on the open sets, because these open sets were in kind of direct correspondence with the vertices and the edges, we can just put them on top of the vertices and the edges. So it's kind of much simpler, right? So yeah, basically what we have is a graph with some extra structure on top. So for each vector, vertex v, we have a vector space f of v. So in this case, this vector space is just like the real plane, so R2. That's what these boxes are meant to show. Then what we have is another vector space for each edge. So that's the vector space you see in the middle of this diagram. And for each vertex incident to an edge, we have a linear map between these spaces. So the vector space of the vertex to the vector space of the edge, and we have that linear map there. And the terminology is that these vector spaces are called stocks, and these linear maps are called restriction maps. So the name restriction maps comes from what I was saying before. It's kind of like zooming in on some smaller subset, and you restrict your view to that. So that's where the word restriction comes from. So these are sheaves, and I'm gonna explain a bit further the intuition behind them. So there's this very nice paper by Hansen and Greist where they provided a nice mental picture about these objects that comes from opinion dynamics. So essentially, you can think of the vector features of the nodes as a space of private opinions. So each node in this network is like a person, right? And when there's an edge between them, these people communicate. So person V and person U communicate in this case. And the vector space in the middle is called the discourse space. So it's kind of the space where their opinions meet and they start discussing. And how this works is basically these linear maps we have, which are essentially just some matrices. They map a private opinion in the discourse space for each of these two participants in this case. And then these participants can kind of compare their opinions in the discourse space, right? So essentially, these linear maps are kind of explaining how the private opinions of these people manifest in the discourse space. And it's kind of a bit like in practice, right? Because in public, we don't say always what we think, and we kind of filter our thoughts, right? And this is what these matrices are doing. They just transform the private opinions into public opinions. All right. And once we have this sort of structure, this sort of sheaf, we can construct what's called a Sheaf Laplacian. So I believe you're probably familiar with the graph Laplacian. And actually, the graph Laplacian is a particular case of Sheaf Laplacian. But let's talk about the Sheaf Laplacian and see how it looks like. So if we kind of, so it's just a matrix, and if we apply it to a vector x, and then we look at node v, what happens? it's defined as you see in this diagram. So we just go for all the, we sum over all the nodes U that are neighbors of V. That's what that notation says. And then we do this kind of very potentially weird multiplications. Well, it's actually not that weird. So if you look at what's going on in this bracket, that's just kind of the difference between the public opinions of the two neighbors, right? So the first matrix times xv is just the public opinion of node V, and the other term is the public opinion of node U, and they just take the difference. So how different are our opinions? And you do this along all the edges or all the neighbors U around V, and then you aggregate them back, but you transform them through this kind of matrix transpose. And the diagram below kind of explains how this matrix looks like. So if you look at the diagonal elements, you will have this sum you see on the left. And if you look on the right, you see this how this like a typical non-diagonal block looks like. And to notice also that this is a sparse matrix. So we have just zeros. These blank regions are just places where there's no edge between the nodes. And something we can do is we can also be like a normalized version of this Laplacian. So we just take all the blocks that are diagonal here, we put them in this matrix D, and then exactly like with the how we normalize the graph Laplacian, we normalize this thing. It's the same kind of formula. And importantly, as I was saying, when D is 1, so D here is the dimension of these vector spaces. I should have mentioned, so all these blocks are D by D. If so, for instance, before we had R2, so these blocks would be 2 by 2. But if D is 1, so all these vector spaces are just kind of a scalar, basically, we're back in kind of the usual setting. So each of these blocks just becomes 1 by 1, and essentially we obtain the graph Laplacian. So if you look at the formula in the definition, if all these matrices you see here, if they're just a scalar 1, you just get xv minus xu, which is exactly the formula for the graph Laplacian. So you can see how we can kind of get more general things in this sheaf formalism. And here's another way to kind of think about these things. So in differential geometry, if we have something like a manifold, we have what's called like a bundle. So this is kind of a vector bundle. So this is just a way to put some vector spaces at each point on the manifold. And one example is just the tangent bundle. So essentially, you put all the tangent spaces at each point and you kind of stick them to the manifold. And once you do that, there's this notion of parallel transport in differential geometry. So what's that? Essentially, if you have a tangent vector at a point, like here, so if you look in the kind of bottom left of the diagram at this vertex W, so we have this kind of relatively vertical tangent vector. If we do parallel transport, we can sort of move it very smoothly along this edge and move it up in this other vector space. And from that vector space, we can move down again and so on. So it's a way to transport tangent vectors. And what these matrices are doing in the sheaf, you could think of just being like a discrete or like sampling some points on this manifold. And these vector spaces are kind of like these tangent spaces. And these matrix multiplications are just moving a vector space from one tangent space to another. So it's kind of like a discrete version of parallel transport. So just a way to move things from one tangent space to another. And if you look at these kind of matrix expressions you see in this diagram, they're actually exactly like these non-diagonal terms you have in the Laplacian. So essentially, these non-diagonal terms are just specifying a way to move vectors from one stock to another, one tangent space to another, depending on how you think about it. Okay, that's just to give you some intuition. It's not like super important if some things are not very clear here. Okay, now let's actually start using these sheaves and do some interesting things. And what we want to do is study the expressive power of this what's called the sheaf diffusion process. It's exactly the same differential equation we had before. Like it looks almost identical. The only difference compared to heat diffusion is that the Laplacian is different. So now we have a sheaf Laplacian instead of the graph Laplacian. But remember, the graph Laplacian is just a particular case. So this gives us some flexibility to study all sorts of diffusion processes. So by just modifying the sheaf structure, we have different Laplacians and different diffusion processes. And what we aim to do here is to kind of study what happens when we try different sheaves there, and can we use them in a useful way. And just to kind of visualize how this matrix multiplication looks like in this differential equation. So on the left, we have this minus delta F, the normalized Laplacian. It has the block structure we were seeing before. And now our feature matrix looks a bit different from kind of the classic case. So we have these blocks that are kind of d-dimensional. So each, because each feature is kind of a point in these vector spaces we were mentioning. So if our vector spaces are d-dimensional, then we have d-dimensional vectors. And that happens for all the nodes in our graph. So if we can just stack them vertically, and that's a single stacked vector containing all the features of all the nodes. And obviously we can have multiple feature channels. So that's kind of going from left to right. We just have multiple columns, and each column is a different feature channel. And each row are all the d-dimensional vectors belonging to a single node. So now the diffusion equation is a bit like, if you think about these vectors, these d-dimensional vectors like vector fields, instead of kind of diffusing scalars, so before we just had like a single scalar like the temperature or something like that, now we kind of diffuse vector fields, which is much more interesting, right? And you could think of the scalar case as a particular case, like when these vectors have dimension 1, so they just become scalars. So that's kind of the intuition. And there is kind of like some minimal thing we can say about this diffusion process, because it's kind of like a classic result. So if we just run this diffusion infinitely long, what happens is essentially we project the initial conditions, so what we have at time 0, into the kernel of the normalized Laplacian. So remember from linear algebra, the kernel of a matrix is just all the vectors that matrix maps to 0. So basically, in the end, we end up with this feature matrix that when we multiply by delta F, we get 0. So all the columns multiplied by delta F yield 0. So that's all that means. Okay, any questions so far? All right, I'll just go on then, but yeah, feel free to interrupt if you have questions. All right, and then what we want to do is we want to see how different classes of sheaves can linearly separate the nodes of a graph in the infinite time limit of their diffusion process. So just to kind of illustrate that with the picture, we start with the graph like you see on the left. So if you look at diffusion time 0, basically, so that's just kind of our initial conditions, right? So we have this graph, the colors denote the labels of the nodes, and the position of each node is kind of its features. So each node has 2D features in this case, and I've put each node at the position indicated by the features, right? And what we want to do is find a sheaf such that when we run this diffusion process, like you see here, in the infinite time limit, these classes becomes very nicely clustered, and we can linearly separate them. So that's great, right? Because it's kind of like what we want to achieve. We want to classify these nodes in this graph, so we can find these sort of diffusion processes that help us do that. So if you look at what happens at diffusion time 14, for instance, which is already a good approximation for what happens at infinity, because this process converges kind of exponentially, we see all these clusters are very nicely formed of different classes. All right, now let's just do that. So first, let's look at some sheaves where these vector spaces are just the real line, so just R. And we also impose some symmetry constraints. So basically, for each edge E, we want these restriction maps to be equal along that edge. So remember, for each edge, we have 2 matrices, one on the left and one on the right. One for the first node, one for the second node, and we just constrain now, well, now there are scalars because we work in dimension 1, right? So we just want these scalars to be equal. And you can show this is actually equivalent with kind of having weighted graph Laplacians. So these are just Laplacians where you put some edges, or some weights on top of your edges. And the weights here will be just the product of these 2 scalars. So you can show that. I'm not doing that here, but just to give you an intuition about what we're looking at. We also constrain these scalars to be different from 0, so we don't want to have zeros there, just to start with. So this is kind of very simple class of sheaves, and they recover weighted graph Laplacians. So yeah, think of these as diffusions with weighted graph Laplacians. And you might think, okay, I've said in the beginning that this heat diffusion was kind of very limited, you can't do much. But maybe you think, okay, if I put at least some weights on the edges and we make it a bit more general, like this weighted heat diffusion, it might do reasonably, right? And to some degree, it does well in some settings. So for instance, if we consider all connected graphs with two classes, so just A and B, two sets of disjoint sets with the two classes, and we have this property that for each node in the first class, A, there exists another neighbor in the same class. So we just assume in one of the classes, any node we look at, we can find a neighbor in the same class. And that's kind of like a homophily assumption, right? We expect to have at least some degree of homophily. We can always find another node with another label in our neighborhood. It's not a very strong assumption, but it is like some degree of homophily that's assumed. Then we say that this class has linear separation over all the graphs in this class. So what does that mean? It means for any graph you give me in this class, I can find your sheaf in this class we defined above. We do diffusion, and we always separate the classes for almost any initial condition. So almost virtually any initial condition you pick will separate the classes. So essentially, this model can kind of do perfectly on these types of graphs. Okay, but here's something else that happens if we just have bipartite graphs with two partitions A and B, and we also constrain these partitions to be equal. So this is the most heterophilic graph you can think of, right? Because every neighbor has a different label from you, right? Like, because in bipartite graphs, you're connected to things in the other partition, and basically everything around you looks different from you, has a different label. Then you can show that there's no sheaf in this class that can linearly separate the classes of any graph that looks like this for any initial conditions. So whatever graph you give me from here, whatever initial conditions, I cannot find a sheaf in this class that can separate the classes. So you can already see that this kind of heat diffusion processes are already kind of struggling whenever we have heterophily in the infinite time limit. So if we diffuse infinitely long, so in this kind of oversmoothing sort of regime. Now, we can actually fix this quite easily by considering more general classes of sheaves. So how does that look like? So now assume we have, again, a connected graph with two classes. So no other assumptions, just any graph that's connected. And we can construct a sheaf as follows. So still we're still with D equals 1, so that didn't change. And first, basically for each, so for the first scalar along each or matrix, here's a 1-by-1 matrix, just to kind of make sure we're all on the same page. Just set it to minus alpha E. So alpha E is just some constant you pick for each edge E. And if the first node is in class A, and choose alpha E if the node U is in class B. And this will look kind of like with alpha E being positive. So, okay, what does that mean? So we're kind of like in this diagram you see here, where the first kind of matrix is negative. So I just put alpha E to be 1 in this case, right? So we have minus 1 and 1. And what happens when you diffuse, you will reach like a state where these features are polarized. So that's kind of what diffusion will do. It will kind of polarize the features. So this orange node will have kind of this feature that's negative in this vector space. And the blue node will have this feature that's positive because they need to agree in the discourse space. So what diffusion kind of does is as you diffuse, these nodes these people start to agree in the discourse space. And because of this kind of different signature, the only way for them to agree in the discourse space is one to have negative features and the other to have positive features. So because of this polarization, you'll have one class have negative features, one class have positive features. And it's very easy to separate them, right? You just look at, 0 is your threshold, right? If it's less than 0, it's in one class. If it's more than 0, it's in the other class. So this is kind of the intuition for this result. So this type of sheaf can linearly separate the classes of any such graph, so connected with two classes, for almost any initial conditions. So we can already see, like, it doesn't matter. We don't need any homophily, heterophily assumptions or anything of that kind. Whatever graph you give us, we can solve this problem. All right. Now there's still kind of an issue here, and that's kind of specific to having these dimension ones. So far we only looked at kind of one-dimensional vector spaces. So our Laplacians were kind of just regular matrices. They are not block matrices so far. But if we just stick with this, we have some problems. So we have a connected graph with more than 3 or at least 3 classes. And if we set all these vector spaces to have dimension 1, then no sheaf can separate the classes for any initial conditions. And why is that? Essentially, you can show that what you end up with is kind of like a one-dimensional kind of a kernel, right? So we said we convert into the kernel of the Laplacian, and you can show when d equals 1, the kernel is at most one-dimensional. So essentially, you're projecting everything on a line, and in the most fortunate case, you're going to end up with something like this, where kind of different classes are placed in different regions of this line, but still you cannot kind of separate them linearly, like at least not with a single hyperplane, right? You would need multiple kind of hyperplane or multiple thresholds. So for instance, for the blue class in the middle, you would need kind of a hyperplane on its left and a hyperplane on its right to separate them. So you're kind of a bit limited, or you need slightly more complex decision boundaries. So you can only achieve this kind of pairwise linear separability in the most fortunate case. So the solution is simply to increase d and use basically that will also increase the dimension of the kernel space. So essentially, we kind of have more room to kind of move in the infinite time limit. And that kind of extra room offers us some representational width to do more interesting things. So one way to do that is to look at d-dimensional vector spaces. And for these matrices, these restriction maps, now we're just going to consider some very simple class. So we say they're invertible and diagonal. So just diagonal matrices, essentially. And now we have these results. So again, we can have any connected graph, but now with any number of classes, C that, let's say it's at least 3 as before. Then if we just set this dimension to be at least C, then this class has linear separation over this set of graphs. So basically, if we make D big enough, we can easily find sheaves that can separate even more than 2 classes. So any number of classes we have. So we also solve this problem. So essentially, we can kind of find sheaves for pretty much any problem. Now, a question you might have is that these diagonal restriction maps are, kind of simple. So, what happens if we perhaps use some more complicated maps? So, for instance, something we could do is consider these bundles I was mentioning. So, in this bundle case, when you have these discrete vector bundles, you restrict by definition. That's what it means to have these matrices to be orthogonal matrices. So these are D by D matrices that are orthogonal. And again, what you can show here is you can kind of make more efficient use of your space. So if you have D that's 2 and 4, then you can classify up to 2D classes, right? So you can kind of use less space to classify more classes. And to give you like an example, again, here's an example of diffusion process. Here we have 4 classes and we're in 2D, right? And we can find a sheaf that kind of clusters all the classes like this, and we can linearly separate all these 4 classes if you look at the lost picture. So that's kind of like, let's say, a visual proof of this result, at least for D equals 2. All right. So that's kind of the end of the theoretical part. And my main takeaway from here is that different classes of sheaves induce diffusion processes with different capabilities. So we sort of seen how going from some very simple sheaves that kind of give us weighted graph Laplacians or very simple things like that, but those very simple things are commonly used in practice. We can see that in that setting we're quite limited. But as we make these sheaves increasingly general and more complicated, we have kind of more power to do other things and to solve other kinds of problems. So This is a bit like in geometry, where if you have like different geometries for some manifold or whatever, you have kind of different types of diffusions on that manifold. So that's kind of the intuition. And also something very important to mention is that essentially any node classification problem can be reduced to performing diffusion with the right sheaf, right? So basically, for any node classification problem you have on a connected graph, I can always find a sheaf that will kind of solve that classification problem. I just put the sheaf over the graph, run diffusion, I can separate everything. This doesn't mean it's easy to find that sheaf, but in principle, you'll always have such a sheaf, which is something useful to know. Okay, now we're kind of moving on to more practical things and seeing how we can actually use the sheaves in practice. So something that you might wonder is, like, where do we get these sheaves from? Or no one gives us a sheaf, right? Like, we never have a sheaf data set. Like, we always have graph data sets. So someone gives us a graph with some features on top, but no one's ever going to give us a sheaf structure on that graph in general, right? So then there's a natural question: how can we actually make use of all these things with that limitation in mind? And what we are proposing in this paper is to learn these sheaves. So we just learn them from the features and from the structure of the graph. So how do we do that, and what does it exactly mean to learn a sheaf? So what it means to learn a sheaf essentially is just learning these matrices, right? Like for the vector spaces, you just pick some d, like beforehand, like a hyperparameter. So again, in this image, d equals 2, because these are kind of two-dimensional boxes, vector spaces, right? And once you pick your d, all that's left to do is decide what these matrices should be. So this FVE and this FUE for each edge E, right? And what we can do is we can just take a parametric function, and it will be a neural network in general. So like this phi here that you see in equation 3, and this is matrix values. And what it's going to do, first, it takes as the first input the features of node V, and as the second input the features of node U, and it will produce you a matrix. And that will be the matrix on the left, so this FVE. If you swap the order of these two things, it will give you the second matrix, the matrix on the right, so this FU triangle E. And that's it, right? Like we can just take this function and we go at all the edges in our graph. We plug in the features of the nodes that form that edge, right, on the boundary of that edge. And we just get all these matrices for all the edges, and that's it. We have our sheaf structure. And perhaps one way to think about this in maybe more familiar terms, it's a bit like in graph attention networks, if you're familiar with that model. So there we also have a function like this here, but it's just scalar valued. So it gives you the attention coefficient instead of a matrix, but we kind of generalize gap in some sense to matrices, right? So now we output matrices instead of scalars. So that's kind of the intuition. And once we do that, what we can do is we just build a model where these sheaves are learned from data, and we just let gradient descend to learn what's the best sheaf for us to solve the task. So it's kind of like what's the best geometry or what's the best structure sheaf structure we can put on top of the graph to solve our problem. And what we use as a model is a kind of generalized sheaf diffusion process. So this looks a bit like what we saw before with the sheaf diffusion equation. We've just put some extra stuff on top, similar to how GCN was adding some extra stuff on top of heat diffusion. So we put some matrices, this W1 and this W2. And now, actually, if you just kind of ignore this Kronecker product in front of the matrix XT, it's exactly like GCN. It's the same formula, right? We had just the matrix on the right, features, and the Laplacian, and the nonlinearity. So all that kind of change is that we also have this kind of additional matrix. And the reason we have it there is because now, if we work in some dimension D, we have d-dimensional vectors. And we can also multiply those d-dimensional vectors with this matrix W1 from the left. So that's all that's doing. So it allows us to have like a slightly more complex linear transformation for the features, but that's pretty much it. Like it's very similar. And in practice, we discretize this equation. So we just work with kind of this more kind of residual network type of architecture. Again, this is just a discretization in time of the previous model, and it looks very similar. And so basically the features at layer t plus 1 are the features at layer t minus this expression we had before. Now, the very important thing to notice here, where this kind of sheaf learning part that I've mentioned shows in, is there's another difference with regard to the Sheaf diffusion equation. You can see that this f also depends on time or on the layer. And the reason for that is because we learn the sheaf at time t as a function of the graph and the features at time t. And this function g is actually what we saw on the previous slide. So essentially, you just take the features you have at time t, you plug them through this function phi I was showing you before. You get all the matrices. Once you have all those matrices, you can build a Sheaf Laplacian, and then you can kind of just use this model. So that's the big picture. Okay, so let's look at some results. So first, let me show you a synthetic experiment where we kind of test this opinion polarization or like feature polarization I was showing you before. So we have a bipartite graph, again, with two equal partitions. And we saw that in this setting, weighted graph diffusion cannot solve this task. So at least not with 100% accuracy. It might do well, but not 100% accuracy. So that's the theory. And what we're doing here, we are just considering a very simple model. So actually, we just use like the model from equation 4 here, but we just set these matrices W1 and W2. They have been set to identity. So basically just get rid of them. And let's just kind of have like a sheaf diffusion process where the sheaf is learned. That's all we're doing here. So kind of a very simple version of our model. And for the baseline, we have this weighted graph diffusion. So similar model, but we just picked these sheaves we were saying in the beginning that you d equals 1 and you have this equality for each edge, just so we get like a weighted graph and a weighted graph Laplacian. So that's the line you see in blue for the weighted graph. And you can see that on the training data set, the blue baseline is doing pretty badly. And also in terms of test accuracy is also doing pretty badly. And the axis here is diffusion time. All right, and you can also see like with more diffusion time, performance seems to get worse for the blue baseline. But for the kind of sheaf diffusion baseline, this orange line you see here, you can see that performance improves as time increases. So you could think of time here as a proxy for the number of layers, right? So with kind of deeper times, we have like kind of more layers in some sense. It's kind of like a continuous layer. And we can see that we can sort of address, at least in this setting, this oversmoothing problem, right? Like we just stack so many layers, like more time essentially, and performance gets better, doesn't get worse. And what we're also showing here in this green line, it's what we call an oracle sheaf. So that's just using a sheaf like in the result we saw before, where we used like a different sign for the two scalars. So we know that kind of sheaf solves this task, right? Because we have this result. So we can just plug it in our model. So instead of learning the sheaf, let's just use this ideal sheaf. And we can see it obviously does perfectly and better. But the kind of learned version is actually also kind of keeping up pretty well with the green line. So the green line is kind of like the ideal scenario. So we can see with learning, we can do pretty well as well. And also to kind of look at kind of the interpretability side of things and seeing what sort of Laplacian that we learned here, what sort of sheaf basically we learned here. Is this kind of matching our intuition? In the last figure, I'm just plotting basically just the product between those two matrices you have at each edge. In this case, they are scalar because d equals 1. So I'm just plotting that product. Now, before training, you can see because of how these weights are initialized and everything, they are sort of clustered around 0, and you have kind of like a typical histogram you see for kind of randomly initialized values. But after training, and we look here at this time that got like 100% accuracy, just seeing what happened there, you can see that all these products are negative, which means that they have opposite signs, right? So like one scalar is positive, the other is negative, like we saw in one of the drawings before. And we saw that they actually recovered this intuition that we had. So essentially, what the Sheaf is doing is learning to polarize the features of the two partitions. So it's actually doing exactly what we would expect it should do. And it can very easily solve the problem by figuring this thing out. And other graph neural networks can kind of struggle in this sort of setting, just because kind of their kind of underlying sheaf structure that's implicit. They use these very basic sheaves that we saw in the beginning. They can't solve it. Okay. And we also have some real world evaluation where essentially we look at a bunch of node classification data sets ranging from very low homophily on the left, so very high heterophily basically, to a very high homophily on the right, or very low heterophily. And our baselines are kind of highlighted in bold here. And we have three versions of these models I've shown you. So we have first a model that learns these diagonal restriction maps. We have a model that learns orthogonal maps. And we also have a model that just learns any matrix. So just an arbitrary matrix, we don't restrict it. And we just plot here kind of the results. So the best result is in red, the second best is in blue, and then the third best is in this purple color. And we can see that in pretty much all the heterophilic data sets, these models are actually doing very well and outperforming existing models. Many of them have been designed for heterophilic graphs actually, and others have been designed for kind of oversmoothing and these sort of things. And at the same time, we're also kind of doing reasonably well on the homophilic benchmarks. So those are kind of the last three benchmarks where the homophily level is quite high. And in general, I think these models are in the top 3 models for pretty much all the data sets except for Cora. So these kind of very interesting theoretical insights have led to some very simple but practical models that actually work in practice. All right, so that's all I had to say. I also have a bunch of references here for if anyone wants to kind of check the details of some of the papers behind this work. I guess we'll have a way to disseminate the slides later and you can check this out. So yeah, that's all I had to say. Thank you for your attention and for the invitation to speak. And yeah, if you wanna reach out offline to me, here are my contact details. I'm also very active on Twitter and happy to take any questions you might have right now.